We're doing the Dirac Equation. So remember, we're doing the quote classical Dirac Equation. It's not been quantized yet. Four-component complex field. Take the index to go from 1 to 4. Don't confuse it with a space-time index. It's a spinor index, alpha. And the Dirac equation is the following. Gamma mu are 4 by 4 Dirac matrices, which are defined by the following relations. You have anti-commutation relations, and you have hermiticity conditions. Any set of 4 by 4 matrices. So mu and nu are space-time indices that go from 1 to 0, 1, 2, 3. Any set of 4 by 4 matrices that satisfy these conditions are Dirac matrices. And different choices of Dirac matrices are physically equivalent. So just recapping what we did last time. Then, of course, there is the adjoint field, which is defined to be psi dagger gamma 0. So remember here that we're just working at a classical level of psi is a 4-component column vector with complex entries. So psi, just to make sure, those of you who weren't here, those of you who have forgotten, psi dagger is a row vector with these entries. So this is a row vector, gamma 0, so you've got a row vector times a 4 by 4 matrix, another row vector, and so on and so forth. So sometimes you can get a bit confused. We're going to be promoting psi to an operator. And what's going to happen when psi is an operator? So just because psi dagger here is being used to denote the Hermitian conjugate at this level of matrices and column vectors. When psi is an operator, psi dagger is the Hermitian conjugate for an operator. So just to maybe it'd be a good idea if I mention this now, is when we look at the operator Dirac field, when you have the operator Dirac field, you have a 4-component vector whose entries, instead of being complex numbers, they are operators that need not be Hermitian. So what happens when I take the Hermitian operator, spring break I suppose, when I take the Hermitian conjugate of the Dirac field, what does it mean? You're sort of doing 2 Hermitian conjugates at the same time. You're doing the Hermitian. This becomes a row vector. But here you have, instead of being the complex conjugate, you take the Hermitian conjugate of the operators. Sorry, I've written that a bit squashed, but anyway. So this is at the classical level. This is at the quantum field theory or operator level. the Hermitian conjugate of the Dirac field is a row vector of these operator entries, for each of which you take the Hermitian conjugate instead of the complex conjugate. So there's a kind of, the book doesn't explain this. Thank heaven you have me here to explain it to you. Okay, so it's just, the book, you just see all the two kinds of Hermitian conjugates all muddled up. But anyway, there you go. And of course, often if you're just writing it in terms of components, if you're just working with components, and sometimes if as I mentioned last time, if you're unsure, just write down everything in terms of components. And then of course, it's clear that if you've got each component is an operator, and I can take its Hermitian conjugate, and everything is clear. But anyway, okay. So we also wrote down. So just to catch up with where we were last time, we wrote down the Lagrangian density. Hang on. So the adjoint field. All right, trivially, if psi obeys this equation, then the adjoint field obeys the following equation. Writing like this: d mu psi bar, and I can write gamma mu plus m psi bar is 0. So if I take the Hermitian conjugate of this equation and multiply from the right-hand side by gamma 0, you should get this equation, or it's just equivalent. All right, so the Lagrangian density for the Dirac field that we wrote down last time looks like the following. Lagrangian density is equal to I, prefer to write it h bar psi bar I psi bar gamma mu d mu psi minus m psi bar psi. That's the Lagrangian density for the Dirac field. And I gave you a homework problem to do over the break. So the Euler-Lagrange equations for, so you can look at each component, psi alpha and psi alpha bar. So you should know, those of you who are still maybe, what do we mean? So we've defined psi bar to be psi dagger gamma 0. What do we mean by psi bar alpha? Just to make sure no one is confused. What do we mean by psi bar alpha? We mean the alpha component of psi bar, all right, which is just the alpha component of this here, which I can write as, so I can write this as psi dagger beta gamma 0 beta alpha summing over beta. Okay, I hope that is, have I got that right? Yeah. So, so of course you're looking at psi bar is etc. times a 4x4 matrix, gamma 0, and so I'm summing over the entries here, multiplying by the row index here. And anyway, I hope that should be clear. I hope it's just sort of matrix, standard matrix. So of course psi, and then of course what is psi? What is this quantity here? Psi dagger beta. It is just psi beta star. Okay, so at the end of the day, alpha psi beta star gamma 0 beta alpha. Now, if you're in doubt, there's nothing wrong with writing out everything in terms of components. And maybe at the beginning, the first time you start playing around with these equations, maybe it's better you do. But once you get used to it, you see, you know, this shorthand, it is easier and quicker to just write down equations without components, and then when you need to, maybe expand them out in terms of components. So, all right. Okay. Anyway, just to make sure we know what we're talking about. So we're varying the Dirac. So by the way, something I wanted to mention, someone sent me an email and worried about what we need to know about the Dirac field. You're going to see that actually there's very little you need to know about the Dirac equation in this sense. You remember when we did, in fact, maybe I shouldn't tell you this now, you think, so I don't have to listen to this. But you do need to listen. But just to say, don't get too frightened. You remember when we quantized the Klein-Gordon equation? The only thing we needed to know is that it had a complete orthonormal set of solutions, which for the Klein-Gordon equation was just, you just needed to know that this was a complete set of solutions. We expanded the field operator in those terms, and that was actually the only property of the Klein-Gordon equation that we used, that these are a complete set of solutions. Similarly, when we did the electromagnetic field, we had a complete set of solutions that looked like this, where these were three vectors with certain orthonormality properties. What we're going to find for the Dirac equation is that there are solutions U and also V PR times e to the same exponential, where the U's and the, so these are analogs of these things, but instead of being three vectors, these are four component column vectors, they're spinors. Okay, I'm going to show you their properties, that there's a complete orthonormal set of solutions of the Dirac equation that similarly are plane waves, but where in front of the plane wave, instead of having a three vector as you have in the electromagnetic case, you have a four component column vector that is just a complex spinor. And that's actually, and all you need to know, these spinors obey certain orthonormality properties. And that's actually all you really need to know about the Dirac equation for the purpose of quantizing the Dirac field. Of course, you also need to know how to express what are the expressions for the canonical momentum, the energy, the charge, and all those things, which we're going to be doing today. So, but you don't actually need to solve the Dirac equation, except you just need to know that there are these plane wave solutions. That's all we're going to be using. So anyway, I keep going off on tangents here. The Lagrangian for the Lagrangian density for the Dirac field, you treat psi alpha and psi bar alpha independently, and you should have obtained the Dirac equation plus the adjoint. The Euler-Lagrange equations for psi and psi bar imply the Dirac equation and the adjoint equation. I mean, this is just basically the Hermitian conjugate of the Dirac equation. There's no independent information here. It's like saying, you know, I have the Klein-Gordon field, and then I have the equation for its complex conjugate. There's no new information here. Okay, it's just a Hermitian conjugate of the Dirac equation. It's just convenient to write the Lagrangian density in terms of psi and psi bar, and to consider psi and psi bars independent fields for the purpose of the variation in the Euler-Lagrange equations. All right, anyways, we've got an Euler-Lagrange equation for, we've got a Lagrangian density for the Dirac equation. So this is where we were last time, and let's move forward, onwards and upwards. So, what do? We've got the Lagrangian density. So, we can look at the canonical momentum density conjugate to psi. So what we're going to do, let's look at it one component at a time. Let's look at the momentum density conjugate to psi alpha. So this is the canonical momentum density conjugate to psi alpha. So I'm taking the alpha component of the Dirac field. For instance, alpha is 2. What is the canonical momentum density conjugate to psi alpha? All right, well, if you look at the, this comes out to be equal to I psi dagger alpha. Now you might want to check that. The only term that contains time derivatives is this first term here. The only term that contains time derivatives is this term here. Okay? So mu is going from 0 to 3. When mu is spatial, there's a space derivative. So it's just the first term. This is the only term that contains a time derivative. And notice that this, we've written it in the compact form without indices. Let's just remember that psi bar is psi dagger gamma 0. And so we've got gamma 0, and d0 psi is, of course, just psi dot. Now remember from your gamma matrix gymnastics that gamma 0 squared is 1. So this is I psi dagger psi dot. Now, what does this mean? This is, if you write it out in matrix form, this is psi 1 star, psi 2 star, and this is psi 1 dot, psi 2 dot. Okay, we've got this column, it's an I times, we've got a row vector times a column vector. I might write this instead as follows. I could write it as, using a summation notation, I could write this as psi dagger alpha, psi dot alpha. Where I'm summing over, the repeated index is summed over. Alpha goes from 1 to 4. All right, it's the same thing. Or of course, psi dagger alpha is just psi alpha star, the alpha component of psi dagger. I'm going through this meticulously, just the first few times we meet this sort of thing, because you're not used to all of this notation. But look, it's just a compact notation. So anyway, so I psi dagger psi dot. This is a row vector times a column vector. This is just I psi dagger alpha component times psi dot alpha component, summing over the alpha component. All right. So what I can say is, well, the only relevant term. So the only term in the Lagrangian density containing psi dot is this term here, which is I psi dagger alpha psi dot alpha. So let me just bracket that off. Okay, it was just this term here with gamma, with mu is 0, which is equal to this. The gamma 0 squared is 1, so it's equal to this. And I can write it, writing it in terms of row and column vectors is never going to be convenient, but maybe if that's what you're used to thinking about, you might want to think about that in the background, but for actually doing the algebra, it's better to write this in terms of, okay, let's introduce an index and use the convention that a repeated index is summed over. So this is what it looks like. It's just the sum of terms, the alpha component of psi dagger times the alpha component of psi dot. This is the term in the Lagrangian density that contains time derivatives. If I now take the partial derivative with respect to psi dot alpha, I'm just left with this here, which is exactly that. It's I, the alpha component of psi dagger, which you just write without the bracket. It's understood that you know, it's assumed that you know what you're talking about. Okay, all right, so everything okay? Any questions about that? So you're going to need to get used to fiddling around with these. So all the ideas are the same. You know, how to quantize a Dirac equation, apart from the anti-commutation thing, that there's a twist that we're going to talk about later. But apart from that, you know, you expand the field in a complete set of plane wave solutions. There are some coefficients in front, in this case, of 4-component spinors with certain orthonormality properties. But once you've got that straightened out, it's all the same stuff, the same kinds of ideas as before. It's just that, you know, you've got all these different components, and you need to get used to this with the multi-component field and the matrices and all this stuff. All right. So, any questions? Okay. All right. So we've got the canonical momentum density conjugate to psi dot alpha, and now what about the canonical momentum density? So let's now look at the canonical momentum density conjugate to psi bar alpha. Now this is often usually denoted pi bar alpha. Now here you have to be careful. This is, okay, let me just say what this is. This is denoted pi bar alpha, but you have to be careful. Some of the notation is terribly sloppy and confusing, but it's standard notation. But what is this? It's the partial derivative of the Lagrangian density with respect to psi bar alpha dot. Okay, just like any you know, the canonical momentum density conjugate to any field is, by definition, the partial derivative of Lagrangian density with respect to the time derivative of that field. Okay, so now if you look at this, well, the Dirac Lagrangian density contains time derivatives of psi, but there are no time derivatives of psi bar. Okay? There are no time derivatives of psi bar. So this is 0. So this is 0. The canonical momentum conjugate to psi bar is actually 0. Now here, there's a potential for confusion, because remember we defined psi bar to be psi dagger gamma 0. So you might think that, well, obviously pi bar is pi dagger gamma 0, and seeing as pi from there is I psi dagger. All right, pi leaving off the index, pi is just I times psi dagger. And you might think, okay, so I've got pi dagger, so I've got minus I psi, minus I psi, but hang on. Then that would be a problem with the, that would be a problem writing it as components. Hang on, here you have to be careful. Hang on, you have to be careful. This is a row vector. If I wrote it like that, no, become a column vector. This is not, I would have to think about it in terms of components. All right. Let me, hang on. Let me write this. You might think that the alpha component of pi bar is going to be the alpha component of this, which is not 0. Seeing as pi has these components that are not 0, you might be tempted to think, oh, okay, pi is not 0, so I can construct pi bar from pi, and I get something that's not 0. What's going on? Well, okay, the answer is that this is not right here. This is just a notational device. You say, here's the momentum conjugate to psi, you call it pi. The momentum conjugate to psi bar, you call it pi bar. But that does not mean that pi bar is given by this expression. This is the definition of psi bar, but there's no kind of general bar operation that you apply to pi. This is a bit like, well, it's just an unfortunate notation. What you would really want to do is you could have written, pi, instead of the subscript alpha, you could have called it pi. Here is what a proper notation would have looked like. You see, well, why do we write this silly notation? Okay, this is what you should have done. You should have said, well, look, let's take the canonical momentum density conjugate to psi alpha. That would be this thing here. The canonical momentum density conjugate to psi alpha is equal to this. And then the canonical momentum density conjugate to psi bar alpha is this here that's 0. So this here, this is the correctly written quantity. It's the canonical momentum density conjugate to psi alpha. For shorthand, we write it as pi alpha. This canonical momentum density conjugate to psi bar alpha, for shorthand, we write it as pi bar alpha. Okay? But don't think that pi bar is given by, pi bar is not pi dagger gamma 0. Okay, that's not I hope that's clear. So sorry, it's just an unfortunate notation. But anyway, all right. So now where are we? So we've got the canonical momentum densities conjugate to psi and psi bar. So now we can write down the Hamiltonian. We can write down the total physical momentum. So here we have your first homework, well no, your second homework problem for the Dirac equation. So remember, we have expressions derived. You know how to, whenever I have a multi-component field, you'll remember this expression that we did way back when we were doing Lagrangian field theory. I have a set of fields. Remember, we were saying we had a set of fields, phi r, where r is just an index. I have any number of fields. These index could label the components of maybe the components of maybe I've got a complex field and its complex conjugate, or it might be components of a vector field, components of a spinor field. Here we've got psi alpha. Alpha is 1, 2, 3, 4, and we've also got psi bar alpha. And of course, for psi bar alpha, the canonical momenta vanish. But anyway, so think of this, go back and think, okay, remember our general Lagrangian field theory. We had a set of fields, were labeled by an index. Here's an example. We have our set of fields is the components of the Dirac field, the components of the adjoint field. Here is the general expression for the Hamiltonian. it's R is a repeated index summed over. You sum over the canonical momentum density times the field minus the Lagrangian density. Work out homework, so this is homework. Show that the expression that you get looks like this. This is the Hamiltonian for the Dirac field. It's psi bar minus I gamma j dj plus m psi, or I don't like the way the book writes it like this, so you might want to just write it like this, minus I psi bar gamma j dj psi plus m psi bar psi. Minus I. Okay, so notice that there's no time derivative. No time derivative. So there's a time derivative appearing in the Lagrangian density, but it gets cancelled by, so let's see, what are the field phi, hang on, where does that go to? Now you see, it's amazing. I've been talking complete nonsense for 5 minutes and nobody has said, Professor, you've missed off a time derivative. Did no one notice? Maybe I did it on purpose to test you. Is that all right now? It's a sum, it's a momentum. Okay, so it's canonical momentum density times the time derivative of the field summed over minus the Lagrangian density. Is that okay? Is that right now? Or is it the second time derivative? I'm getting all these blank looks. Okay, you should, this is it. I think this is it. This is what spring break does to you. So anyway, so what happens when there's a time derivative appearing in the Lagrangian density? You've got one of these pi's, there's something odd here, that the canonical momentum density is unusual in that it's not equal to the time derivative. There's no time derivative. I haven't been thinking, he made a mistake here. There's supposed to be a time derivative here. No, there's no time derivative. Okay, the canonical momentum density conjugate to psi dot is just I psi dagger. There's no time derivative. So because of that, when you multiply all these terms, there's a term here that's proportional to the time derivative that cancels the time derivative term of the Lagrangian density. Anyway, this is the Hamiltonian for the, please check that through, and you can also check the physical momentum, total physical momentum. So this is the general expression for the total energy. There's a general expression for the total physical momentum that comes from, when we studied the Lagrangian field theory for the case. So more homework. Check that when I have a set of fields like this, that the general expression for the total physical momentum for the Dirac case looks like the following. We have a momentum vector. Maybe let me write it over there. Let me write it over here. So, total physical momentum is P is equal to minus I times the integral over all space of psi dagger grad psi. Okay, just from applying the general expression that we had. So there's an integral, I can't remember exactly what the general expression looks like, but it's something like pi r grad phi r, something like this with a minus, I don't remember. Anyway, it involves an integral over there's a canonical momentum density in psi, which you see is just our I psi dagger, and there's a grad psi, and the canonical momentum density for the adjoint part is 0. So anyway, go back and check that the general expression for the total physical momentum reduces to this here. All right, fantastic. So now there's the question of the angular momentum. All right, so I'm going to give you the short version. So remember, the expressions for angular momentum they come from Noether's theorem under invariance under a Lorentz transformation. All right, so so this is the way we wrote the general infinitesimal Lorentz transformation. If we ignore the part that contains a translation, instead of a translation, ignoring the translations in space and time, just boosts and basically general rotations in space-time. So boosts and spatial rotations. So what do we get? There is a question, well, how does the Dirac field transform? So Lorentz transformation of psi. So if you're interested in the details, you can look in the book in the appendix. It's a bit fiddly, the Lorentz transformation of the Dirac field. I'm just going to write you down the result because it's just something, all we're really interested in is to know what is the expression for the intrinsic spin angular momentum. So, but if you want to go into it more, so here is the, under a Lorentz transformation, the Dirac field transforms, let me write it up here. So here we have a Lorentz transformation. So this implies that psi alpha of x, the Dirac field, transforms into a new field at the new space-time point x prime, or the new, well, written in terms of the new coordinates x prime, so this is a change of coordinates, sorry, I should write x mu prime. Okay, I'm changing the coordinates. And how does the Dirac field transform? It transforms like this. Where these so the epsilon mu nu's are just these infinitesimal quantities that appear in the Lorentz transformation. What are these quantities here? So what we do is we define, so sigma mu nu. So note here, there are sums over repeated indices. So here, mu nu and beta. So mu nu are space-time indices that go from 0, 1, 2, 3. Beta is a spinor index that goes from 1 to 4. All right. So what is sigma mu nu, what is this quantity? Sigma mu nu alpha beta is equal to this is just the alpha beta. So here I've got a 4 by 4 matrix. Sigma mu nu is a 4 by 4 matrix. And this quantity here is the alpha beta component of that 4 by 4 matrix. What is this 4 by 4 matrix? It is equal to, it's defined to be I over 2 times the commutator of the gamma matrices. So our gamma matrices are some given 4 by 4 matrices that obey those anti-commutation and hermiticity properties we wrote down at the beginning. The commutator of the Dirac matrices times I over 2 defines a new, for each mu nu, there is a 4 by 4 matrix, and the alpha beta component appears in the Lorentz transformation law for the Dirac field. If you're interested in looking at the details of this, I can recommend looking in the book as the appendix. We're not going to need it in this course. We're not going to be doing any Lorentz transformations of the Dirac field. Why we're interested in this is that you will remember that we have a general expression for the angular momentum and intrinsic spin of a field that depends on, remember we wrote down way back, we wrote down the Lorentz transformation of a general set of fields in this kind of form where there was some arbitrary coefficients here. And then we had an expression for the intrinsic spin in terms of these arbitrary coefficients. So if you go back to the chapter on the general Lagrangian field theory and look up what was the expression for the intrinsic spin of a field in terms of the coefficients that appear here in the Lorentz transformation. Go and look it up, do a bit of homework, and you should be able to write down the following expression for the intrinsic spin vector of the Dirac field. Let's call it S, and it is equal to the integral over all space of psi dagger. Let's write in an h bar over 2 to make you feel that you're seeing something familiar. The integral over all space of psi dagger h bar over 2 sigma times psi, where sigma, what is sigma? It is a set of 3 matrices, but these are 4 by 4 matrices. 4 by 4 matrices, which are equal to the following. Sigma 2, 3, maybe I should write these with an upstairs index. Sigma 2, 3, sigma 3, 1, sigma 1, 2, which are, so the appropriate components, these 4 by 4 matrices that come from commutators of Dirac matrices. 2, 3, 3, 1, and 1, 2. These define 3 4 by 4 matrices that let's write them as if they're, I've got a vector matrix, let's put them together as the 3 components of something that I'm going to write as if it's a vector. And if I multiply, so there's a 4 by 4 matrix times psi, which is a 4 column vector. So this is a 4 column vector times this. This is a row vector times a column vector, gives me a number. This number is a function of position in space. I integrate over all space. That is the intrinsic spin vector of the Dirac field. Now, these are generalizations of Cowley matrices. Now you might ask, what is so in the Cowley matrices, Cowley spin matrices are of course 2 by 2. You might ask, there's something you might want to check if you're interested. Again, if you look in the appendix, I'm not going into this because we're not really going to need it, but if you're interested, you might be thinking, hang on, what's the connection actually with the Cowley matrices? These are 4 by 4 matrices. Cowley matrices are 2 by 2. You might suspect that, well, is sigma is maybe equal to, so our 4 by 4 matrix, we've got a set of 3 4 by 4 matrices. You might think, well, maybe these are equal to the Cowley matrices, which are 2 by 2, multiplied by 1 0 0 1. In other words, what I mean here, sorry, that's a bad way of writing it. It makes it look, what I mean is, okay, sorry, no, okay, let me write it like this. What I mean is the following, sigma Cowley, 0 0 sigma Cowley. These are 2 by 2 matrices. If I think this 0 here, I really mean this is a 2 by 2 matrix. These are 2 by 2 matrix. These are 2 by 2 matrices. These are 2 by 2 matrices. So you might think that these 4 by 4 matrices are basically just the same as the sigma Cowley, but just with an extra number. This is actually true in what's called the Dirac-Cowley representation. So remember that there are different representations of the gamma matrices. The gamma matrices only have to satisfy certain anti-commutation and hermiticity conditions. And different representations are physically equivalent. There is a certain choice. When I say a representation, I mean a certain choice of Dirac matrices. It's called the Dirac-Cowley representation, for which this is true. For that choice of Dirac matrices, if you calculate these quantities, essentially they're just the same as the Cowley matrices, but just as written as 4 by 4 matrices. So it's just, if you're curious. So they're generalizations of the Cowley matrices, and so there you are. And so this is the expression for the intrinsic spin of the Dirac field. Finally, one more conserved quantity, the charge of the Dirac field. So our Lagrangian density which, all right, let me write it. Lagrangian density is invariant under phase transformations. Phase transformations. So psi e to the I epsilon and under these phase transformations. Infinitesimal phase transformations. So where epsilon is a small constant. So it's just the same thing. Remember when we did the complex Klein-Gordon field? It's the same thing again. invariance of the Lagrangian density under phase transformations implies conservation of charge. Remember, we had a general expression for the charge. We wrote down for a general set of fields. If we assume invariance of the Lagrangian density under phase transformation, we had a general expression for the conserved charge. Go back and look up that expression. Plug in the case where the set of fields is the Dirac field, and you should obtain the following expression for the charge, which is some constant, let's call it Q, times the integral over all space, psi dagger psi. Psi dagger psi. That's the expression for the total charge of the Dirac field. You may also remember that there is something that I'm not really going to use now, but let me just also mention. You remember that the charge Q comes from this is a continuous symmetry that implies a conserved current. Conserved current ds alpha. Well, hang on, no, that's right. ds mu. Why am I doing that? D mu. S mu is 0, where Q is the integral over all space of the time component of the current, which is just a density. Okay, just recalling the general formalism, you remember that the invariance of the Lagrangian density under continuous symmetry implies a local conserved current like this, and if you integrate the time component over all space, you get your conserved quantity. Anyway, you may be it's just interesting to note the conserved current. What does it look like? It looks like the following. So this has, you can think of it as rho J, as it has a density and a spatial current. And this is what it looks like. It is equal to Q psi bar gamma mu psi. I'm writing, we're not going to be using this at the moment, but later on, when we do the interaction between the Dirac field and the electromagnetic field, there's going to be a term in the Lagrangian density of the form some constant times A mu S mu. Okay, basically the four-dimensional inner product of this current with the vector potential. That is the interaction term. That is how the Dirac field interacts. In other words, this is, if you like, this is the electric charge density and current that you put in effect in Maxwell's equations. So we did the quantization of the free Maxwell field. If you add in a charge and a current on the right-hand side of Maxwell's equations, in the case of the Dirac field, the charge and the current looks like this. This is the charge density and the current density of the Dirac field. Okay, it's a charged field. So we'll come to this later when we do the interaction with the electromagnetic field. This expression will come up again. For the moment, what matters are the expression for the total charge, the total intrinsic spin, the total physical momentum, and the total energy. All right, so let's see. Good. Blah, 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 blah. All right. So, before I move on, are there any questions? Any questions about this? Any questions?
Is your sigma, is it always block diagonal, or is it just in this?
No, that's in, is it always block diagonal?
Is it only in this Dirac polarization?
Well, hang on, I mean, here we're defining, a vector matrix with just these three components. We're just taking these three components from, and I've omitted it now, but these three components of sigma mu nu, we're writing them as a vector matrix with just three components. So there are just three components. So is that what you mean? Or?
So this 4x4, I guess I'm not understanding this notation. So sigma is a 4x4.
So hang on, now you're getting me confused. Hang on, did I write this? Have I written this correctly? Alright, so what this means is let's just look at, say, sigma 1. Let's just look at sigma 1. And in the Dirac-Cowley representation, it is equal to sigma 1 Cowley 0, 0, sigma 1 Cowley. Now, one of the achievements in life that I've always aimed for, always failed to do, is to memorize the Cowley spin matrices. But anyway, sigma 1 Cowley is a 2 by 2 matrix, which I'll just write like this. Okay, I don't know what the entries are. The 0 here, what I mean is 0, 0, 0, 0. Here's 0, 0, 0, 0, and again the sigma 1 Cowley. Let's call these A, B, C, and D. Okay, I don't remember. There's 0, there's a 0, there's a 1 and a minus 1, and I never remember what it is. But anyway, so this is just the X, or if you like, the X sigma Cowley matrix. So this is now a 4 by 4 matrix, and this is what sigma 1 is equal to in the Dirac-Cowley representation. Okay. And as I said, we're actually not even going to use any of this really, but well, slightly, a little bit.
So the relation between the sigma is composed of your sigma 1, 2, and 3.
Sorry?
The relation between sigma and sigma 1, 2, and 3 is composed. It's kind of expanded in this basis of your larger 4x4s.
Sorry, I didn't follow.
So what is sigma? It's composed of these 4x4s, like a linear combination.
So when you say sigma, do you mean this here?
Yes.
So each component of sigma is, these are the components of sigma. Where this sigma 2, 3 here, this is I over 2, gamma 2, gamma 3. Okay, I take the commutator. Gamma is a 4 by 4 matrices. I take the commutator, that's a 4 by 4 matrix. So that is what sigma 2, 3 is equal to. So I've got 3 4 by 4 matrices. Okay, maybe should we talk about this maybe when we meet this week, or?
Okay.
Yeah? Any other questions? No questions? No. Okay, so let's see if I can give you a quick 10 minutes of what you really need to know, actually, for the purpose of quantizing, is there is the question of what do the complete orthonormal set of solutions of the Dirac equation look like? Complete orthonormal set of solutions of the Dirac equation. So, here's what you really need to know. To quantize the field, we're going to expand the Dirac operator in terms of a complete orthonormal set of solutions. Here is a set of complete orthonormal solutions. So remember, as usual, we do we're working in a volume V with the periodic boundary conditions and the usual sort of allowed momenta. These three integers, these are integers, V is L cubed. So it's just like before, but with K replaced by P. So it's just a traditional notation that when you're dealing with bosonic fields, you use K to label the momenta. When you're dealing with the fermionic or massive fields, more traditional. The fermionic field is more traditionally used P. It's just a convention. Anyway, so what do they look like? For each allowed momentum, there is an energy E, which you can write with the subscript P if you prefer. That's what the book does, which is the square root of m squared plus p squared. And the Dirac for each P. So having introduced that notation, so for each P, for each allowed P, the Dirac equation has four independent solutions, which look like they're written as follows. UPR. So that's right. Okay, 1 over root. All right, I'll follow the way the book writes it. E to the minus I. E dot x over root v. And VPR. E to the plus I. Dot x over root v, where r is an index 1 or 2. There are four independent solutions. Now, what are these u's and v's? So U and V, U's and V's are constant spinors. When we say constant spinors, we mean they're a four-component complex spinor whose entries are just constants. They don't depend on position or time. And they satisfy, U and V satisfy the following. Gamma mu, P mu, minus M, UPR is 0, and gamma mu, P mu, plus M, VPR is 0. Now, some people like to introduce the notation, one of Feynman's little inventions, P slash, which is defined to be gamma mu, P mu, and similarly A slash for any 4 vector, so basically the contraction of a 4 vector with a gamma matrix. This notation, I don't see it used much anymore. I mean, this book uses it a bit, but I don't know how it seems to have fallen out of use, this notation, so I'm going to avoid it. But if you notice it in the book, if you wonder what the heck is that, that's all it is. It's just a shorthand for this. Anyway, why do they satisfy this? Well, clearly, if I assume that psi is, for instance, UPR e to the minus I p dot x over root v, and I substitute into the Dirac equation, it has to be a solution. We want this to be a solution of the Dirac equation. This here we've just got a constant spinner times a plane wave. So you know that, well, let's substitute it in and use the fact that, well, d mu, if I take the d mu, the mu derivative of e to the minus I p dot x, what do I get? I get minus I p mu e to the minus I p dot x. So substitute is, if I think of this as a trial solution, I substitute it into the Dirac equation. I take the derivative of the exponential part. That implies that, well, what does it imply? It implies this here, that u has to satisfy, because remember here, there's an extra I, so I gamma mu d mu psi is going to be, I gamma mu d mu e to the minus I p dot x. So I times minus I is 1, so I get gamma mu p mu minus I p dot x. Remember that the u's, the components of u does not depend on positional time. So anyway, maybe check this through, check that you're happy with this, that if I write a trial solution of the Dirac equation, u is, it's a 4-component spinner whose entries, the entries depend on E and mod P. They depend on the energy, they depend on the value of the momentum. We can look at some, if you're interested in some examples, the examples, the expressions depend on the representation of the gamma matrix. If you're interested in seeing what these things look like, you can look in the appendix of the book. Okay, but the point is they're constant spinners, their entries depend on the energy and the momentum. The only properties that we're going to need of these U's and P's are certain orthonormality properties that we'll look at next time. But if you say, okay, I have a constant spinner times a plane wave, let's have that to be a solution of the Dirac equation, you should be able to check that, well, okay, so U has to satisfy this equation here. Notice this equation does not contain position or time. This is just a matrix equation. For a given P, the components here are just the momentum and the energy. These are the gamma matrices. Okay, this is a matrix equation for U. You can find a solution for U. It's just some 4-component vector whose entries depend on the energy and the momentum, and whose exact form will depend on what representation you use for the gamma matrix. And none of that, all we're going to need, let me carry on from here next time. But so we're looking at plane wave solutions for the Dirac equation. We have constant spinners U and V. The constant spinners U and V are solutions of these two matrix equations, and they have entries that depend on the energy. All we're going to be interested in, so let me just show you that the parallel is that the U's and the V's are the analogues. You remember, so here we have the Dirac field. These are analogues of, you remember for the electromagnetic field, we had these little polarization vectors. And the plane wave solutions that we used to expand the field were equal to these little polarization vectors times plane waves. So these quantities, the U's and the P's, are analogues of these things here. Now if you go back and you think, which properties did we use of these? The only properties we used was that they are orthogonal to K, okay, and that they are orthonormal. This was equal to delta RS. Okay, for a given K, epsilon K1, K2. So basically they form this little, and so hang on. Yes, so R is 1, 2. R is 1 and 2. R is 1 and 2. So you've got K, you've got epsilon K1 and epsilon K2. They're orthogonal to K, and they're orthogonal to each other. That's all we use, the only properties we used of these things. There are similar orthonormality properties. So these are orthonormality properties of these polarization vectors. There are similar orthonormal, when I say similar, they're a bit different, but anyway, orthonormality properties of the U's and the V's, which are actually all that we're going to need when we do the quantum field theory, okay? So I'll go into those next time. For the moment, go over all this, check that you understand what's going on here. These are constant 4-component spinors, obey these matrix equations. If you're interested, look up in the appendix for the example of the Dirac-Cowley choice of Dirac matrices. You can actually look at some examples of what these 4-component spinors look like, but actually the only properties of them that we're going to use are the orthonormality properties that are analogous to these properties here. Okay, so any questions? Okay, please do the homework. Please derive the conserved quantities, and we'll continue on Thursday.